we good? Okay.
Okay, we're starting the next part of our workshop. Our next speaker is also joining virtually. It's Elise Wonderful. Elise is a senior researcher at Microsoft Research Amsterdam, working on the reinforcement learning and deep learning for molecular simulation. Your research interests lie in AI for science and structure, symmetry, and equivariance and reinforcement learning and machine learning. Before joining Microsoft Research, she earned a PhD on the topic of symmetry and structure and deep reinforcement learning in the Amsterdam Machine Learning Lab. Before the PhD, she studied artificial intelligence at the University of Amsterdam, where she obtained a master's degree in laude. Her master's degree was on the subject of deep reinforcement learning for coordinating traffic light controllers, and she was also involved in illusory AI research. Thank you, Elise, for joining us virtually. We're happy to hear our talk.
Thank you. Yeah, thank you for the. Oh, can I start?
Yes, please do.
Okay, great. Thank you for the invitation. I'm very sorry that I couldn't be there in person today, so I hope that this will still be somewhat engaging for you in the room there. I've been interested in symmetry reinforcement learning for a while, but I haven't focused on it lately. So I thought it might be a nice way to get back into what's going on by giving a little bit of an overview talk of what's been going on in the field recently. And I'm not a roboticist, but I'm more of a reinforcement learning person. This might all already be very familiar to you, so I won't spend too much time on the motivation for reinforcement learning. For me, I really see it as learning behavior, trial and error. Sorry, I get a little bit of an echo.
Sorry, we can fix that. Give me just a moment.
Yeah.
Is this your charger? Please try again, but let me know if it's back, okay?
All right. Yeah. Yeah. So reinforcement learning, I find it very interesting because it's, in principle, it has the biggest promise out of all of machine learning, right? It's about really acting intelligently in the world, learning from trial and error, and improving over time, and actually doing decision making, not just predictions. And this has, of course, the promise of applications everywhere, as in autonomous driving, rescue robotics, but also it turns out that there's quite a lot of applications in, for example, the natural sciences. However, a lot of these super nice applications are somewhat hindered by the fact that in practice with reinforcement learning algorithms, we tend to require an unsustainable number of trials, which means interactions with the world. And that is fine if your simulator is very cheap, for example, as you would have in video game AI. But for example, in the sciences, simulators are very expensive. And in other cases, as I imagine in robotics, actually taking a sample costs actual real-world time. So you have to wait quite long if you need a lot of samples. Additionally, there can be quite a high real-world cost for failed trials, as in the case of this robot that drove into a fountain, and they probably have to buy a new robot. So reinforcement learning in kind of the vanilla case is not very data efficient. And it's kind of a long-standing challenge in the field to try to solve the data efficiency problem. And the approach that we took there is to look at, when are two states the same? So for example, in bipedal locomotion, you can take the very simple observation that if you know how to walk in the left direction, in general, you don't have to start from scratch if you want to walk in the right direction. But in a somewhat slightly less obvious case, I got my driver's license in Amsterdam in the Netherlands, where they drive on the right side of the road. So now if I want to visit my colleagues in Cambridge, where they drive on the wrong side of the road, I don't have to go and get a new driver's license. It's assumed that I know how to generalize to driving on the other side of the road. These are the kind of things that we were interested in putting into reinforcement learning algorithms. Symmetry. So to go over the reinforcement learning notation real quick, just so that we're on the same page. In general, in reinforcement learning, we're dealing with some agent that takes actions that I'll denote as A, usually indexed by time. These actions influence the world or the environment in some way, which results in a state S, also indexed by time, that's observed by the agent. The agent also receives from the world a reward or feedback signal that's usually defined by the designer of the world or the problem that we're trying to solve. And based on these observations that the agent does, it uses its policy pi to predict a new action, which then again influences the world. So we model this as a Markov decision process usually, or MDP, which consists of a space of states, a space of actions, and a transition and reward function. Now the transition function gives us, for a given state taking an action, the next state that the world will end up in. This can be stochastic or deterministic. And similarly for the reward function, we have a state in action and we get some kind of feedback signal about how happy are we to be in this state. Now the transition and reward function together is what I will refer to as the MDP dynamics. The goal of reinforcement learning is to find some policy pi star that maximizes the cumulative reward. So if we go through this loop again and again and sum all the rewards together, we want to maximize this sum of rewards. The policy, by the way, I will usually denote as pi. When we're talking about symmetry, we usually talk about symmetry groups. A group is a mathematical object, but some examples of symmetry groups are, for example, the group of translations, which is like shifting, for example, an image up and down and left and right. Reflections, which is just flipping. And also rotations, for example, the group of 90-degree rotations. Now, mathematically, a group is a set, for example, a set of rotations with a binary operation. In many cases, this is composition, so putting two elements of the group together, that obey the group axioms. So that means identity, there's an identity element, the 0-degree rotation. Invertibility, so for every element in the group, its inverse is also in the group. If we can rotate to the right, we should also be able to rotate to the left. Closure, which means that if I combine two of the elements of the group with the operation, the result should also be in the group. And associativity, which just means it doesn't matter where we put the brackets. Now, at the risk of being a bit superfluous, given the name of the workshop, I want to just make sure we're on the same page when I'm talking about equivariance. In equivariance, we're usually talking about equivariance under a group. So we're saying that F, a map from one space to another, is equivariant if the following holds. I have some input X, in this case it's a dog, and if I form some group operation on this dog, for example, I rotate it, and then I map it with F to latent space, I should end up at the same point as if I were to map the latent space first, and then transform there. So in this case, the X is the input, is the picture of the dog, but it can of course be anything you want. And then when I'm talking about an equivariant network, I usually mean that F in this equivariance constraint is defined to be a neural network. And usually this network is made equivariant through weight tying. For example, if we're looking at 90-degree rotations, what we might do is have one filter and then all the 4 different rotations of that filter at the same time. Unfortunately, I don't have super much time of going into how these equivariant networks work. There are a lot of good tutorials online if you're interested. Now, when I'm talking about symmetries in reinforcement learning specifically, I mean the following. So for all states and actions in the Markov decision process, and all elements in the symmetry group that I'm interested in, I want that the dynamics are invariant under group transformations. So let's take this example where we have a diagonal symmetry. Here the group transformation might just be flipping over the diagonal. Then I want it to be the case that for all states and actions, the rewards are invariant under group transformation. So that means if I compute a reward of taking action A in state S, this reward should be the same as if I take rotated action or a flipped action in the rotated state or in the flipped state. So as an example, that would be state A and B here that I got from this older Ravindran paper. If I'm in state A here, my goal is to get to G, and I move up, that should give me the same reward as if I'm in state B here and I move right instead. I can say something similar for the transition function. So the probability of going to S prime from state S taking action A should be the same as the probability of going to state GS prime. So the rotated next state should be, this probability should be the same as coming from rotated S and taking the rotated action. In this case, rotation would mean something like going from state A to state B and taking, instead of action up, I rotate to action going to the right. And if I know how to do this, then I can kind of fold my MDP into a smaller version of it. And this smaller version is, of course, easier to solve. So it might be easier to find the optimal policy in a smaller MDP because there's just fewer solutions. I can do this because if SA and GSGA are symmetric state action pairs, then that means they have the same optimal policy pi star. As a quick reminder, I want to remind you what a homomorphism is. So a homomorphism is a structure-preserving map between similar algebraic structures, such that the following holds. If I map two elements of a space with F to a different space, and then I operate on them there, I want to end up at the same point as if I operate in the original space and then map the results with F to the other space. So this already sounds very similar to an equivariance constraint. An example of a homomorphism that you're probably familiar with is a linear map between vector spaces. Now, an MDP homomorphism is just an instance of a homomorphism where we're mapping from one MDP to another MDP. One MDP is the original MDP for our original problem. In this case, that's card pull, which, if you're not familiar, is a Markov decision process where we're trying to move a card left or right in order to balance a pull that's on top of it. So if my pull is kind of falling like this and I'm moving to the right, that's kind of the same as if my pull is falling here and I'm moving left. So an MDP homomorphism is a map from this ground or original MDP to a more abstract MDP, where I've kind of folded over the symmetries in my state action space. So this again gives me a reduced problem that's hopefully easier to solve. And again, if SA and GA are symmetric state action pairs, then they have the same optimal policy. So what we did in NURBS 2020 is publish a paper on MDP homomorphic networks, which is kind of saying if you have the symmetries of your problem, you can define an MDP homomorphism, and that behaves in such a way that it's quite easy to build an equivariant neural network to obey these constraints. So in the card pull example, what we would have is we have a state, and if we flip it and then compute the optimal policy, we should end up at the same point as if we compute the policy first and then we swap the left and right action. Now, if you write down your policy in kind of a vector form, then you can quite easily define an equivariance constraint of the type that you often see in kind of standard machine learning papers on equivariance, which is that if I compute the policy of a transformed version of my input, it's the same as permuting my original policy. So what these MDP homomorphic networks do is they exploit symmetries in reinforcement learning. What this gives us is improved sample complexity. So in all these plots, higher is better, it's the average return. And on the x-axis, we have a number of interactions with the environment. And in these problems that are honestly quite simple toy problems, leveraging the symmetry has resulted in fewer interactions with the world to get a similar performance compared to unconstrained networks, but also to data augmentation, for example. Now, experimentally, this is not super convincing, but there's a lot of follow-up work that has found similar improved sample complexity in other settings, also more complex settings, and also in robotics, of which I'm sure you're already aware. So branching out from this original point, there's kind of a lot of different interesting directions have been going on, but unfortunately I only have like 20 minutes to cover this, so I had to focus on some things. And I decided to focus on two topics that are the most common questions I get when I give talks. So one is, what do I do if the symmetries are not completely exact? So you can imagine if you have a bipedal robot, it's mostly a symmetric problem, but maybe there's some noise in your, I don't know, motor on one side, which means that you're just slightly asymmetric. So how can you leverage symmetry in that setting? The other is, what do you do if you don't know the symmetry? Either you know it, but you don't know how to write it down, or you just don't know it at all, but you suspect that there's something there. So those are the two things I'll focus on today. So what if the symmetries are not exact? So some work has looked at what do we do, what happens if we enforce exact symmetries in problems that are not fully symmetric. And empirically, this hurts the performance of these equivariant models, which makes sense because we're enforcing an exact symmetry, whereas the actual problem is not exactly symmetric. And in some of these experiments, they also show that the more you increase the asymmetry, the more you decrease the performance. So Sinkovich has an extended abstract where it makes like a quick characterization of the optimality gap between the optimal value function phi star and the best value function you can get if you enforce symmetry in an asymmetric problem. And this is also dependent on kind of the level of asymmetry. So that seems to match these empirical findings. One thing that I've seen quite a bit, let me move the Zoom thing aside, is the idea of adding either a symmetry regularizer or an auxiliary loss to your standard reinforcement learning loss. So you just add this on top like you would do any regularizer. So there's two main versions that I've seen. One is to have some kind of distance based on this equivariance constraint that we saw before. So we're trying to move the permuted original policy and the policy of the rotated state closer together, but we're not strictly enforcing it. And you can do something similar with your value function, where you say the value function should be invariant to symmetries if the problem is symmetric. Then you can say, I want my value function of my original state and the value function of the rotated state to be as close together as possible. So this does leverage predefined symmetry. So you still have to know the symmetry, and you also still have to know how it acts on the problem. But it does allow the network to deviate from the symmetries if it turns out that a fully symmetric policy is not optimal. Another thing that I've seen in this setting is the notion of symmetry rerouting, is a term that I've called it for now. So what is in the setting of approximate equivariance? This is some work by Mark Vinci from 2021, where they're basically saying, okay, we might have not fully symmetric problems, we might have misspecified symmetries. We want some way to deal with that if the symmetries that we expect are there are actually different or not the way, or they're not there at all. What they do is they have two routes through your neural network. So one goes through a standard restrictive layer that's kind of like a regular equivariant layer with hard constraints. And another route goes through a generic neural network layer. And then the outputs are combined together, but they put a high prior on the equivariant layers and a low prior on the generic layers. So this gives the network strong preference for enforcing symmetry, but allows it to deviate if it turns out that that's not actually what's in the data. They compare this on half cheetah problem, which I think is one of those Mujoko problems that apparently only has approximate symmetries. And they show that compared to unconstrained networks, they're able to leverage these symmetries much better. Another work is on partial equivariance. So that is when only part of your state is symmetric, but the other part of the state is not. The question is, how do you leverage symmetry for the parts of the state that are symmetric? And do you not enforce symmetry in parts of the state that are not symmetric. So an example from this paper is the idea that if you're doing a block stacking task, your blocks may rotate, whereas the robot arm itself is always in the same place, so it does not rotate along with the blocks. So the approach that they take here is based on dynamic filter networks. So in a dynamic filter network, what you do is you allow your inputs to generate filters for a neural network that is then used somewhere else. So what they do here is they have a regular equivariant route as normal, but then part of the equivariant filters in that route are generated through the non-equivariant route. Thought that was kind of a neat solution to the problem. I would also classify this as a symmetry rerouting approach. The second question I very often get if I'm giving talks is the question, what do I do if I don't know the symmetries? Discovering symmetries is kind of a hard problem. If you have a discrete MDP where you know the dynamics, its graph isomorphism is kind of similar to doing a graph isomorphism problem, which depending on your problem might still be doable. But of course, in practice, we have a lot of times not a discrete MDP, and we very often don't know the dynamics. So we want to do something that works in all settings. So some approaches are, if you know, for example, the group, you know that there's a rotation, but you don't know how to write it down, as in this example. If you have kind of a car and it rotates, but you're always looking at it from the same observation point, then you cannot easily write down a neural network constraint on this rotation. But there's clearly a rotation. So what they do is they have a regular encoder into a latent space, and then they enforce the symmetry in the latent space transitions to get like a bit of both worlds in a sense. If you don't know the group either, so it's not just a problem if you don't know how to write it down, but you don't know what it is, or you have a hunch, but you're not certain. This Vinci paper that I presented before with the high prior equivariant, low prior non-equivariant layer, they show some experiments where they outperform untied neural networks, so regular neural networks, even when the symmetries are misspecified. So by learning the weighting, this still works quite well. And I could imagine that you also can throw just a bunch of symmetry groups in there and have the network learn which ones are reasonable given the data. The other one is work by Zand, Rezai, Shostari, where they try to learn these MDP homomorphisms without supplying the group info by doing it kind of in one go with policy learning, by structuring their neural network in such a way that they end up with an MDP homomorphism. And they have some experiments where it does seem like it's recovering the symmetry quite nicely. If your input is symmetric, but your output is not, so for example, your states are symmetric, but in one part of the state space, you want to do something completely different than the other, even though the observation is fully symmetric, you could have an equivariant encoder to make sure that you're able to leverage equivariant representations, and a non-equivariant output, which is one of the things that we did in the NERVS paper. So some open challenges and future directions that I think would still be interesting to look at. So I talked about learning inferring symmetry from data, leveraging approximate and partial symmetry, and also group structured representation learning. One open question is speeding up equivariant networks. So while they're very good for sample complexity, they tend to add some additional computational overhead, especially the more, if you have like continuous rotations, those ones tend to be even more expensive. So there's some work in this area on learning to speed that up. Another thing I find interesting is more semantic weight tying rather than symmetric weight tying. So I can imagine that if you have a bunch of roads with different speed limits, you always want to reduce your speed similarly if there's like a lot of snow and it's very slippery outside. Another thing that I think is quite interesting is moving beyond just permutations for multi-agent learning. So it's very common to say, okay, we have homogeneous agents in my multi-agent system, and I'm going to do weight tying over the homogeneity, which is completely reasonable thing to do. But there's also some works that are looking at other things, for example, at rotational symmetry in multi-agent systems, or at mutually incompatible symmetry breaking in zero-shot coordination, for example. Other line of work is looking at equivariance, in particular in partial observability. So one approach to doing that is to leverage equivariant histories. So say, okay, my current state is, given this observation, is the same if, is symmetric if my entire history is also symmetric. And on my personal level of interest, I would be super interested in looking at more large-scale experimentation and analysis. I'm very curious how differently these things behave at scale compared to unstructured neural nets of the same type. So wrapping up, leveraging symmetries helps improve sample complexity in reinforcement learning, but also related fields. So in general, weight tying is preferred to data augmentation. I see I left this in from some slides I cut earlier. That's also another finding, that in a lot of papers where they compare to data augmentation, weight tying tends to perform better in terms of sample complexity. We also discussed methods for leveraging inexact symmetries and what to do if we have unspecified symmetries. Also went a little bit into open challenges and future directions. I'd be very curious to hear your opinions on this. Thank you very much for listening. And if I missed any papers that you think are super relevant for this, please let me know, because I have another talk coming up end of October and I'd love to include it. Thank you.
Thanks so much for the great talk, Elise. We have time for questions.
Hello, thanks for the talk. I think there is already many well-established methods to make the policy of the neural network equivariant or symmetric. But that does not necessarily make the produced motion or behavior symmetric. For example, if we train a humanoid locomotion task, the robot can learn to exploit either its left or right body part. But the policy is still equivariant or symmetric. Meaning that it does not solve the problem fully. I wonder if you have any insights on that?
Sorry, I'm having a hard time hearing. I also couldn't hear my introduction very well.
Just come up to the. We're coming closer to the mic.
I'm very sorry. Yeah.
Hello, can you hear me?
Oh, this is much better. Yeah.
My question is that we already have a bunch of methods to make the policy on neural network symmetric or equivariant, but that does not guarantee that produced motion or behavior is symmetric. The robot can exploit either the left or right part.
Right.
For example.
Yes.
Yeah. So, what's your opinion on how we should solve those behavior or motion asymmetries?
So if the policy is strictly symmetric, then if we're, I see what you mean. You might have two routes that are equally good, and we're walking
I mean,
only along one.
Like for example, in one episode it links towards left, and in another episode it links towards right, and the policy is still satisfying the symmetric condition.
I think that depends very much on what you define the symmetries over. So if you define, if you enforce the symmetry to be over entire sets of trajectories, then I think it could happen what you're saying. But if you're doing it on the state action level, then if you're in a given state, you would always still have one preferred, let's say you deterministic policy, right? You have one preferred action that you take. Then you only symmetric in the sense that if you flip, if you end up in a symmetric state, you would take a symmetric action. But it doesn't mean that in one episode you go left and the other you go right.
Okay. Thank you.
Does that answer the question?
Yes.
Thanks so much. I think because we're a little behind schedule, we're going to save any other questions for the panel discussion, which will be actually next time. Thanks so much, Elise. Give her a round of applause real quick.